So Didier, what's the issue with this again?
I think if you just open the first slide, go to the view, and then full screen.
Slideshow.
Full screen, not slideshow?
Yeah. That's what you want?
Good enough.
Okay, so the second talk is given by Jim Newton, who is a PhD student at EPITA Research Lab in France. And he's given us some ideas about type checking in heterogeneous sequences. It's yours.
Okay, thanks everyone for coming to hear my talk. I'm going to explain a little bit about the Common Lisp type system, some of the things it can do, and some of the things that it can't do with regard to sequences, and then talk about some of the extensions that we've made to enable what I hope is an intuitive way to describe patterns in sequences in Common Lisp. Okay, so what is a type in Common Lisp? So Common Lisp defines types in sort of a semantic way of any collection of objects is a type. You can specify types with what's called a type specifier. So types aren't first-class objects, so you can't get a type and do something with it. But you can construct an expression which represents a collection of objects, which might be finite or infinite, or it might be empty in some cases. There are some examples of types such as integer, number, and then a user-defined type, ASDEF component. So each of those types describes certain collections of objects. There's a concept of a compound type specifier. The EQL12 represents the set just containing the singleton element 12, the integer 12. You can specify a member of 3 keywords, so this is a type containing 3 particular keyword symbols. The satisfies odd p is a type which contains all of the odd integers, and specifically it defines the type which contains every object in Common Lisp for which odd p returns true. And then you can combine arbitrarily complexly using and, or, and not. So the list of all objects which are either a string or a number and fail to satisfy this user function myfun. There's no guarantee that that is a non-empty set, obviously. It might be empty. There are several ways to describe empty types. The nil symbol represents the empty type. You might talk about the type of all objects which are both a number and a string, which of course no such object exists. Or the set of functions which satisfy, or set of objects which satisfy both even p and odd p, which of course is again the empty set. Types have many purposes, but from a very high level, types are used by the compiler to make your code more efficient in runtime or memory space. And that's typically done with its declare construct. So declaring that x and y arguments of this function are of type vector of floats. But because Lisp is a dynamic language, you can also use type information at runtime in the logic of your program. So type p returns true if my list is an object which is a list of a list length 3 whose third element is a string. So with this type of construct, it becomes a bit difficult, but you can still describe quite a lot. Unfortunately, there are some sets of objects or types that are extremely difficult or impossible to do with the Common Lisp type system. For example, you can't declare a value which is a list of arbitrary length for which all of the elements are a number. The type system is simply not expressive enough to express that. You can specify that a particular element is a number, or that the list is an element of length 5, and all of those elements are numbers. But it's not sufficiently expressive to express an arbitrarily long list of numbers. And there's a common data structure that's used in Lisp quite a lot called the plist, which is the pattern keyword value repeated arbitrarily many times. And you can't express this as in the Common Lisp type system either. So you can't declare your function except a plist as an argument. Of course, you can type this in the comment, but you can't have the compiler check that for you. So I'd like to introduce a how does this work as far as pointing? Anybody know how to point?
Other way around.
Voila. All right. So I want to borrow some notation from rational language theory. If anybody has, probably a lot of computer science people have studied that. But this notation of number with a plus sign as a suffix means that I have a sequence of one or more numbers. And the syntax I'm introducing in Common Lisp is a type called RTE, and the prefix :+ number. And this is just a Lisp syntax for this rational language syntax. So as an example, this type RTE of plus number represents a list of arbitrarily long length of numbers, at least one, but not an empty list. In this case, we have keyword followed by integer, repeated 0 or more times. And that's the syntax borrowed from rational language theory, and the Lisp infix or prefix syntax, RTE of : and then this : cat means concatenated, so some object followed by some other object. And then this pattern repeated 0 more times. And once that type has been defined, then you can use that any way that you can use any other type in Common Lisp. So I can declare the type of plist, which is a list and satisfies this. So basically, RTE matches any sequence, and sequences are lists or vectors, and some lists support other types of sequences, but at least lists and vectors. So RTE of keyword and then the type that's passed as an argument to the def type, that pattern repeated 0 more times. The lists of those and also the vectors of those. But then if I AND that with list, then I restrict it to only the lists of that follow that pattern. And then I can declare a function taking arguments A and B, for which the first argument is a sequence of one or more numbers, and a second argument, which is a plist of floats. So a list of the form keyword float, keyword float, keyword float. And the depending on which Lisp you're using, if you're using Lisp which validates your declarations, then it will at runtime check the values of A and B to assure that they meet those type restrictions. So how do we implement the Common Lisp code behind the type, which actually validates whether the object matches the type or not? Well, again, we borrow from rational language theory that every rational expression can be represented as a finite state machine. The way that the computation proceeds is we look at the first element of the sequence. We ask, is it a symbol? If no, we return nil. We don't match the sequence. If it does, then we move to state 1, and then we ask one of two questions. Is it a number or is it a string? If it's a string, we move to state 3. And then we keep following the state machine, looking at each element of the sequence exactly once. So there's no backtracking. The complexity order of execution is exactly proportional to the length of the list. So we have a linear order complexity of checking whether a given sequence matches the pattern specified. When we exhaust a sequence, if we happen to be in a final state, we return true. If we exhaust a sequence and we're not in a final state, if we're in state 1, when we exhaust a sequence, we return nil. If at any point we have a type for which there is no arrow leaving the state, then we return nil. There's a few ways you might implement in code this finite state machine. You might represent it with class objects with transitions and states and such, and have a sort of a program that walks the state machine and such. Well, what I decided to do was actually dump the state machine into Lisp code, sort of like a macro. There's a couple of extra gotchas that I encountered. But basically the function looks like this, given a function given a sequence. Is the sequence a list or a simple vector or a vector or some other type of sequence? Then the accessor functions are different. You access the elements of a list a bit differently than you access the elements of a simple vector. But once that we've determined that it's a list, then we can dump the code for state 0. It looks like this. We say, are we at the end of the list? If we are, return nil. If we're not, type case on just symbol. If it's a symbol, go to state 1. And in each state, the code looks very similar. There's a test for, is the sequence exhausted? If not, if it is, return T or nil, depending on if we're in a final state or an intermediate state. If there is an element, if the list is not exhausted, then type case on the types which are represented as the transition arrows. So this code is very concise. There are potentially times when the optimizer could optimize this a bit. For example, it might swap the order of some of the type cases, and in some cases, if it determines that to be more efficient. But the code is pretty much as efficient as I could imagine writing it, and straightforward to generate as well from the state machine. An example of when you might want to look at a sequence and ask whether it matches a particular pattern is if you're just trying to decide whether to call destructuring bind on a particular list. If you call destructuring bind on a list and the list doesn't match the format of the destructuring bind, then you'll probably have a runtime exception. So I've constructed this macro destructuring case where you can specify any number of destructuring lambda lists, and if the data that you're given to the destructuring case matches the format of the list, then execute the code within the destructuring bind. So you look at the first case, it's quite simple. So an A and a B and an optional C, where A is an integer and B and C are strings. That actually corresponds to this rational type expression here of an integer followed by a string followed by an optional string. So if the data is in that format, then call destructuring bind just on the given destructuring lambda list. The next case is a bit more complicated and interesting. So the destructuring lambda list is a value followed by a list of two values. A and B are all three fixed nums. And then we have a at key with allow other keys. So we have a key : X, :Y, and :Z with some fairly complicated rules about which things can be repeated and which other keys are allowed. But with the restrictions that X is a symbol, Y is a string, and Z is a list. So you could actually write this. You could actually write this rational type expression by hand by looking at this because it's not very complicated. But expressing this destructuring lambda list as a rational type expression is quite complicated. And destructuring case does that for you. And here's what it looks like. So don't try to write that by hand. But you have some part that represents the required part of the list. And then you have a bunch of cases for all of the keywords being in different orders with the dependencies. And in some cases allowing, where's the code for? Yes. allowing other keys to appear which are not the X, Y, and the Z key. We can represent that as a finite state machine, which is, I think, quite beautiful. It's a matter of taste. It looks complicated, but in fact, if you try to execute it with a given set of data, you would find that you traverse right through the state machine with the number of checks according to the number of elements in the list that you're trying to test its pattern. So even though it's complex, it's always executable in linear time as a function of the number of elements in the sequence. The cases that I showed so far always had the property that the type test leaving a particular state in the tree was unambiguous. If you had a case such that we want to test for integer and number, then you will find that all integers are numbers, so it's not clear which path of the state machine to follow. And this indeed is a problem, because the way, well, for many reasons. For one reason is the model of dumping the state machine just as executable code using tag body and goto really depends on the state machine being deterministic. And this state machine is non-deterministic. We need to follow both and then keep some idea of which paths work and which paths don't, and et cetera. So what we have to do instead is decompose the types into non-intersecting types. So this state machine represents the same as the one before. Either we want to test for integers or numbers which are not integers. And then that's completely unambiguous. In this case, integer is a subtype of number, but you might have types which are not in subtype relationships, but just have overlaps. Can't come up with one so quickly out of my head, but it's very possible to occur. So in general, the problem is, given a set of types, which we can think of as a set of sets, how do we decompose the set of types into disjoint sets, such that the union of those sets is the same as the union of the original sets? And that's it's a non-trivial problem, as it turns out. It's trivial algorithmically, but it's non-trivial in execution complexity. And in the research, we've come up with several different ways of doing this, with advantages and disadvantages, and they work quite well for the number of types that you would probably write in a destructuring case. But when you get beyond 20, 25 types, the complexity of actually decomposing this becomes quite enormous. How is that decomposition done? Well, in Common Lisp, there are some interesting features for the type system, which make it quite fun to work with. We can compose type descriptors or type specifiers just by building S expressions. So the intersection of two types can be expressed with a backquote and substituting the two types in there. So we build a type specifier, which represents the intersection of two types. We can ask if two types are disjoint by asking, is the intersection a subtype of nil? Basically, does the intersection of two types have any object in it? If it does, then the types are not disjoint. And we can ask if two types are equivalent by asking, is each one a subtype of the other? And the subtype P function is a really funny function which returns two values. The second value tells you, was it able to compute the right answer? And the first value tells you true or false in case it was able to compute the right answer. Strangely enough, some Lisp implementations implement this differently, and the specification allows for the algorithm to give up if it doesn't want to do the computation. in implementing the project, I often wish that the type system actually allowed more input from the programmer. I would like to be able to given two of these RTE types, be able to calculate whether one is a subtype of the other, because it's something that you can do with the theory of rational languages. But there's nowhere in Common Lisp to hook into the subtype mechanism. And if you could hook into that, then it turns out there's a lot of interesting things you could do, like in the destructuring case, find dead code paths and eliminate them, or warn the user when the destructuring case has overlapping cases so that it potentially is order dependent. One of the extensions that I would like to do to this is examine whether the concept could be extended to other dynamic languages, or whether this really is really a Lispy concept that you my suspicion is that I could implement this in some language like Python or Scala or even Julia. It's something that I would like to be able to investigate in the coming months. The code is available if anybody wants to download it. The paper and the presentation is not on this site yet, but it will be on that site. Okay, thank you. I'd be happy to answer any questions.
Sure.
Yes, sir.
In terms of equal annotation, what's the actual complexity of jointness calculation?
The question is the disjointness calculation. What's the complexity of that? So there's several algorithms that I've implemented to do this, and it's not. There's one algorithm which I believe I haven't proven yet, but I believe it's an n-square complexity.
The subtype relation undecidable?
Pardon?
The subtype relation undecidable?
It is, yes. There certainly are types for which you can't determine, because it's equivalent to the halting problem, whether they're intersecting. In that case, you decompose by, if you don't know if A and B are intersecting, you consider A and not B, B and not A, and A, and one of those might be empty. But when you check type P of that, you find out that this object is not of that type, which happens to be empty. As far as the complexity of the algorithm, I don't know the complexity of the subtype P function, which is in Common Lisp. I suspect that it has some really nasty complexity because it seems to be very nonlinear. But I haven't looked at the code to see exactly why. But except for the subtype P function, I think is an n-squared type complexity. Yes, sir.
You might want to look at the paper by Baker.
This is actually what I've done. Yeah.
So the disjoint, computing disjoint type strict seems like you're sort of trading off between two different exponential behaviors, right? Converting an NFA to a DFA has potential exponential explosion, but maybe not, right? Have you looked at sort of deciding based on the actual situation whether you decide to just be like, okay, well, let's just pay the NFA cost because the subtypes.
That's a good comment. There are other reasons that I need to use a particular representation of the finite state machine because of the way that I'm converting the expression into a DFA in order to be able to support certain operations like intersection, union, and complement. And the algorithm I'm using that is based on what's called a Brzozowski derivative. And in order to meet the Brzozowski derivative requirements, I need the types to be disjoint as well. I explained that in the paper, but it wasn't really enough time here. But that's definitely a reasonable question to ask. And I might be able to use some other tactic and avoid that and just use some non-deterministic DFA as well. Yes, sir.
How often do those horrible overlapping type things actually occur? It seems to me, based on showed that you gotta have a pretty terribly designed sequence to get something like that. Is that pretty common? Or?
It seems to me that if a human being is going to describe a list with some pattern in there, then you're going to use a handful of types, symbols and strings and numbers, and you may be distinguishing integers from numbers. So my guess is that the occurrence of those overlapping types is rare. But certainly it's easy to come up with degenerative examples. Like I tried to write some test cases just taking, alphabetizing the built-in Common Lisp types, taking the first 2, the first 3, the first 4, the first 5, and decomposing them. And I found that at the limit of between 15 and 20, the machine or the Lisp crashed and I had to restart it. Yes, sir.
What was your original drive trying to solve this problem? What got you into doing this?
The original problem was I had a, not in Common Lisp, but in another Lisp that I had been using before, which didn't have an extensible type system. It had a built-in type system that you couldn't change. I had data coming from a technology group, and the data was in an S-expression format, which described some physical process. And the data was undocumented and changing with every release, because they were trying to come up with the best format to describe this physical phenomenon. And I needed to write code that would extract information out of there. So my code for checking the syntax and conditionally, if it's like this, do this, if it's like this, do this, was really hard to have to maintain, but there was no other way in that particular language to do it. And then when I became introduced to regular language theory, it fit that problem quite well. Unfortunately, I've left that company in the meantime, so I can't go back and apply that technique to the. Yes, sir.
So, just to confirm, the destructuring case macro, do you code both the expression and you read the declarations, right? And you use.
It's a very simple code walker, yes, please.
Do you just read the declaration directly, or do you use some implementation-specific way to extract the declarations?
No, I read the specification of declare and wrote code that implemented that. And if I made a mistake in my interpretation of the declare specification, then there's a bug in the code. Yeah. For example, the Common Lisp specification is unclear to me. What happens if in the same declare you declare the same variable twice with two different types? Is that an error? Do you take the last type, do you take the first type, or do you take the intersection of the types? It's not clear. So, there was another question.
I'm going to take it outside.
Okay.
So,
Could you put the link back up? It went so quick I didn't have time to. Please. Thank you.
Okay, thanks for your attention and your questions.